this is going to be a proposed amateur radio, or I'm sorry, an amateur phased array radio telescope. Let's see how we do here. And the agenda is going to be, I'm just going to have a brief overview of phased array systems generally, and then I'm going to give a description of the telescope. So where does all this come from? And it comes from problems I was having doing radio astronomy. And the telescope on the left is the first radio telescope I built, and it's a 608, 614 megahertz double bow tie total power antenna. And notice I have a little asterisk down there. This is Shad Nygren's great idea. So in about 2008, at the very first Society of Amateur Radio Astronomy Western Conference meeting I went to at Stanford, at the very end of the meeting, just like this, Shad Nygren got up and said, well, you could take, our UHF systems are centered around the channel 37 on the UHF band, and that's a protected radio astronomy band. Why don't we just use off-the-shelf components? And he even suggested this Radio Shack U8000 double bow tie antenna. And so before this, I'd gone into paralysis by analysis mode, and I had spent years literally trying to learn as much as I could do and agonizing over what kind of system. And all of a sudden, it was like the light went off. Why don't I do that? And so, so I did that, and that was the first telescope I built. And because it has a 30-degree beam width, that's a pretty big chunk of the sky. But you can use digital signal processing and that sort of thing, and I'll actually show you some data from it in a minute. But the problem is the issue is with 30-degree beam width, you don't need to be very precise aim because 30 degrees is big in the sky. So later on, I decided to use that same idea of freeloading off of stuff that had already been done, and I repurposed a satellite dish. You can see it's DirecTV, 12.2 to 12.7 gigahertz total power system. And the good news is it was cool. The bad news is the beam width went from, and that's half power beam width, by the way, went from 30 degrees down to 4 degrees. So let's see, let's go down here. By the way, initially, this is the telescope mount I used for doing drift scans. So drift scans, we probably all know, you aim straight south, and then you just go up in elevation, and you let the Earth scan around. So this was the system I was using initially. Went my 611 megahertz. That's what 30 degrees looks like in the sky. So you can be off a little bit. But notice when you go to the 3.7 degrees, it's a much smaller target. And so this led to this problem. So I was trying to just image the sun. And the sun's the brightest radio object in the sky by far. And I couldn't hit it. And it was, so here's why. That little red circle, if you can see that, the little red circle is what I'm trying to hit the sun with, and I'm having a problem. And so you can see I'm thinking I'm aimed at the sky, but I'm not. And this problem is exacerbated by, so it's bad enough with parabolic dishes, but when you have an offset dish, you're not even aimed right off of the dish. So you can see here I am with what they call these things, goniometers, something like that. Anyway, trying to get it to the right elevation, and almost impossible. So it was just frustrating as could possibly be. So that's aiming. The second problem I have is when you do drift scan, it takes a long time. Why is that? Because you're waiting for the Earth to rotate around. So the data on the left here is 9 days worth of data that I took in 2014. And basically I'm looking at the elevation that gives you Cassiopeia, the supernova remnant there at M1. And you can see all the data there. So it's 9 days worth of letting the Earth rotate around. And then you go up at 4 different declinations. So there's 4 times 9, 36 days just to get data here to be able to make an image. And that takes a long time. 36 days is a long time. Oops. So you might say, well, to fix the aiming problem, maybe I could just choose an alt-azimuth positioner. And this is a positioner that was used to aim antennas for a one of those mobile news feeds. And the thing weighs about 50 pounds. It's honking big and expensive. I got it donated to me. So I'm probably going to use that for something, but those are expensive. And then you still have the problem of being able to aim. And even out here, we were out at Owens Valley taking the tour. And, even when you have these other big telescopes, you still gotta aim it. And you don't get good data if you can't precisely aim. So it's still a problem. So what's the answer here? Maybe it's phased array. So I first learned about phased array when I was an undergraduate at getting my physics degree. And I was fascinated by them then. And the idea is that you could put up basically arrays of antennas and there's no moving parts. And I'll talk more about that here in a minute. But one of the challenges to understanding what's going on here is the vocabulary. And I'll just tell you, it's a little bit confusing. So I'm going to try and walk through here some of the things to be able to understand what is what in this area. So there's different types. There's something called an aperture array, and we're going to talk about more about that, also known as the phase array. Another thing is the phased array feed, which is essentially a radio astronomy camera. And then we're going to talk about the difference between an aperture array and a phased array. So just right out of the chute, aperture arrays are looking themselves right at the sky. And as we're going to see, phased array feeds are the device they put at the focal point of the telescope to actually get the signal. So just right out of the chute, this is what a phased array feed looks like. And this is one of the ones they use at the Green Bank telescope. And it's a 19-bit camera. And if you count all those little mini antennas on there, there are 19 of them. And this is put right at the focal point. And so you can kind of think of it as a 19-pixel camera. And I'm not talking about that. So these are very handy and awesomely cool, but that's not this. So we're not talking about phased array feeds. We're going to talk about phased array apertures. So just a tiny bit of history. These aperture arrays were originally developed as part of radar systems in World War II. And here's a picture of these enormous arrays in England. And then curiously, for all the things that Reaver did, he built an array of dipoles in the late 50s, and it had 1 square kilometer receiving area. And I was shocked that I had never heard about this until you look at the frequencies that he was looking at. So it's 500 kilohertz up to 2.1 megahertz. Notice that this is well below the 13 megahertz radio window. So Grote Reber is looking at the bottom of the ionosphere. He's not even getting out of Earth here. So no wonder you never read about this, because it's garbage stuff coming out. Now, I mean, it's a good experiment because people didn't really understand the ionosphere very well. But anyway, it's important that you get the right frequency, as we're going to see here a little bit later on. Okay, so now let's look at some definitions. And so in the antenna community, phased array and aperture array usually mean the exact same thing. So you'll see them interchangeably used. And as I said, when you're talking about either phased or aperture arrays, you're looking straight up at the sky. That's the thing that's actually gathering the photons from the sky. Now I got a couple of pictures down here, and this is the proposed European square millimeter array. And you can see there's a relatively low frequency version on the left, and it's those are those folded dipoles. What's curious is look at the one that's the 500 to 1,000 megahertz one. Those are actually tiles, and they're actually going to fit together, and it's physically going to cover a square kilometer with tiles. And so that's pretty dense. You can't get more dense than covering every, and I'm talking about dense as far as placement, you can't get more dense than covering every single part of that. Over here on the right, this is the HERA, the Hydrogen Epic Reionization Array in South Africa. And you can see it's 14 of these 40-foot diameter dishes. And notice they're all packed closely together. So almost always when you talk about just the phrase, just phased array or aperture array, it's almost always one of these densely packed. Okay, and that's opposed to a synthetic aperture. So what's synthetic aperture? You've got, could be same number of elements or maybe more or less, doesn't matter. The point is it only covers a small portion of the total area. And so in the picture down here, this is the HERA array in South Africa. And you can see down here, this is it down in the bottom, aperture array, and it's pretty densely packed. And up above is the synthetic array, which is a whole bunch of individual disks widely separated. So what's the most, oh, I'm sorry, I got one more slide here on this. So the idea behind the synthetic aperture array, remember this is the widely spaced array, is that there's a whole lot of antennas spaced from one another, and it's going to synthesize a single large telescope. And they're only going to cover a small fraction of the land. Data is collected from each antenna, and then through a process called correlation, we're going to talk about in a little bit, it synthesizes the one big huge telescope. And so when you think about this, the biggest, not the biggest, it may even be the biggest, but the most well-known of these synthetic aperture arrays is the Very Large Array. And so it's got 25 meter diameter antennas. It's along 3 arms of a Y-shaped leg. Each one is 13 miles long. You may also know they have different configurations. So they have the A, B, C, D configuration. When they're in the A configuration, that's the one you always see them in the movie like Contact or 2010. They're all closely bunched right in the center. So they're nowhere near the ends of the 13 meter arms. And then in the B, they move further out, C further out, and then D, they're more or less equally spaced along the 13-mile arm. And so here's pictures of it. And this, in the picture up in the upper left here, you can see they're all in the, this is the A configuration. They're all closely packed in there. So using this technique, so when they're out in the D configuration, it's as though you had a telescope that's 22 miles or 36 kilometers across. So that's a pretty big telescope. And I just only mentioned this idea of antenna efficiency here. And it's the effective area divided by the actual total area of the antenna. So the effective area is a function of the number of antennas, the size of the antennas, and then the aperture area of the antenna is, imagine that you just took like for example, the Very Large Array and divided it, just its diameter across there, whatever its diameter is its aperture area. And when you do this, you see that the Very Large Array, so it's got 25 meter antennas, 27 of them, each 294 square meters. When you add all that up, that's surprisingly 7.938 square kilometers. It's a lot of area. But when you put it out over that 22-mile diameter, it's a tiny, tiny number. It's about 1,000th of the total area is covered by dishes. So what that means is, and resolution, by the way, this is a key part, resolution is dependent on separation of antennas. And so the farther they are apart, the more resolution. And so the Very Large Array is 22 miles across. That'll give you good resolution, but it isn't a very good photon bucket. It doesn't catch photons very well because there's a lot of empty space in there. So how do they solve this? They try and take a large bandwidth so they can collect as many photons as possible, and then they integrate. We're going to talk more about that. So I'm just going to spend a minute talking about interferometry. And by the way, I failed to mention this before, but I feel like I'm on the verge of imposter syndrome here, because no matter how much you know or don't know, you don't know enough. And so I'm going to explain interferometry here. Many of you know it way better than me. And so I hope that my imposterness isn't exposed here.
We're all learning.
Yeah, well, we can hope.
We're all students.
Yeah. All right. So in optical astronomy, most of us know bigger means better, right? So a bigger telescope means you get brighter images, you're catching more photons. also gives you better resolution. In radio or in interferometry, it's synonymous with this phraseology called synthesis imaging. And remember, we're going to synthesize a big telescope with a bunch of little ones. And so in order to, because radio waves are way longer than optical, in order to get Hubble-like resolution, these radio telescopes would have to be huge, many kilometers across. And, you know, we can't make a solid telescope. Remember the one I showed you with the tiles there? That's a square kilometer. I mean, that's unimaginable to me that they're doing that. So you can't fill in all the gaps here. But we're going to synthesize that by putting these individual antennas. We're going to take the data from them. But here's a key point. Because you're taking data and because light's traveling at the speed of light between individual telescopes, it's really important that you have very precise timing. And I'll give some examples of this in just a little bit. So here's some, and you've probably seen these images before, but I created these here. So if you're an object out in space, subject of interest, and it creates an electromagnetic signal, it's going to emanate away from that in a sphere, but as the sphere goes far enough away from it, eventually the surface of the sphere looks like a plane wave. So we're really talking about plane waves coming from the subject of interest. So it's coming from the upper, in the side and the left, it's coming from the upper left. And as they come down, 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 eventually in my example here where I've got two antennas, number one and number two, separated by a baseline, it's going to hit number one at some time. And notice it's this distance A still away from the second one. And so it's at time one, it's going to hit antenna one. At some time later, it's going to go down here and hit time two. Well, what's that time? So it's the time it takes light to go across that distance A. And if you do all the geometry, here's the geometry for what the length of A is. If you divide that length by the speed of light, that'll give you the time difference here. Now there's a special case on the one on the right here where the plane waves are coming and it hits both antennas at the exact same time. So when it does that, that delta T, the time difference, is going to be 0. And the only time that's going to happen is when they come straight overhead and down. But related to that is, imagine that you're tilted only slightly off to the side. There's going to be an angle there. That's what's going to be the mapping resolution of this thing. And I'm going to talk about that a little bit later. So, and I give it this, I know this is super wordy here, but I'm just going to talk through it. So go back to our example here. Imagine that this angle here, so if it's, get my Greek letters here right, rho here is theta, yeah. And then rho, sigma. That's sigma. Theta and sigma. Right. So if sigma here is 38 degrees, let's go back here, and you work out all the math, and I have a 300 meter baseline between my two antennas, the time difference for that is 0.7933 milliseconds or 793 nanoseconds. So, and then if I change it to 45 degrees, I get a slightly different example, and that's 0.7119 milliseconds. So in other words, in order to distinguish between whether the signal is coming from a source at 38 degrees or 45 degrees, notice the difference between these is only a few nanoseconds. And so I have to have timing better than that in order to be able to have the resolution to be able to find those. And then that's with 300 meter separation. If I go to 2 meter separation, notice I'm down here to 5 nanoseconds versus 4.7 nanoseconds. So timing becomes super important, particularly as the baseline gets less and less. And so if I do two-dimensional interferometry, in other words, I put my antennas all along an east-west direction, what's going to happen is my signal, or the pixel in the sky, is going to be narrowed. So you can see it's long in the north and south direction and narrow in the east to west direction. So that's one-dimensional interferometry. If I expand it to 2 dimensions, in other words, I have antennas that not only go east-west, but they go north-south. If I do that, then I shrink it in both directions and I back to my little tiny circle. and I can aim that. And so the size of that, the diameter of that little circle here depends on both frequency and on baseline. So generally speaking, the farther the baseline is apart, the smaller, for any frequency, the smaller that circle is going to be. In other words, the better resolution I'm going to get. If you expand it to 3 dimensions, so where would you get that? So you could imagine that I have a set of arrays that are out here, and because Earth isn't flat everywhere, there's going to be somewhere slightly down in a hole or slightly above. And also, you may be surprised to know, we all know the Earth's curved, but did you know it curves 8 inches in a mile? And so if you have elements that are separated by several miles, now your antennas are going to be down by several feet or meters, and you're going to need to account for that. If you do that, you have to work out this whole correlation equation, which looks ugly. But in practice, here's what you do. And I was surprised to see, when I was looking for stuff to talk about this, here's something that talks about here at Owens Valley, how they actually do that here. And the way they do it is they don't actually work out this calculation. What they do is they look at an object in the sky that they use as a reference point, and then they adjust their timing lags. So in other words, the time difference it takes for a signal to get from one antenna to another, they adjust that until it maximizes the signal. And so that's the practical way they do it, and that's the way it's just done. And so here's the very large array, and it's me drawing in these little things here. But there's 27 antennas, and if you look at antenna pairs, so this is one antenna versus another, there's 351 different antenna pairs. And so I drew them all in here. Believe it or not, that's 351 drawing. And so each antenna acts as its own individual pair. And then we're going to do is we're going to take the data from each one of those pairs, and we're going to combine it together through a process called correlation. And then from that, we're going to synthesize as though this was one giant antenna here. As I said, the resolution is related to the wavelength and separation. But just as a reference point, the human eye has a resolution of 17 arc seconds. So when you look up and you see the moon with your whatever, with your bare eye, that's 17 arc seconds. So just remember that. And I'm just going to throw this in here. Because the Earth's rotating, those pairs that I showed you before, it's as though you get extra pairs, because every time you sample, they're in a different place vis-a-vis the universe. And so actual Earth's rotation helps you in creating a whole bunch of pairs. So instead of 351, it's 351 each time you sample. And so pretty soon you get thousands of these samples.
That's why integration is so helpful.
That's
because you're putting together essentially a different aspected image of the object every time you scan it. And it's going to really help you in the end, because you really get a better picture of that.
Absolutely, absolutely. Okay, so what is a correlator? And I put on here, it's scary. And why is it scary? Because there's a lot going on here, and it's scary. I mean, I just say what it is. Okay, so what does it mean to correlate? Let's just start with that. So if you think about just in not just science, but what is it? It's whenever you have two or more variables, you're trying to find the statistical relationship between these two variables. And so you're correlating them. So if it has a high correlation, that means as one goes up, the other goes up, or could have a negative one. As one goes up, another one goes down. So that's what correlation means. You're trying to find two variables and find out what the connection between them is. Okay, so a correlator, what is it? So it's either a hardware or software device that takes, in this case, it's the sampled voltages off of individual antennas. So remember back to the very large array, you've got 27 antennas, 351 pairs of antennas, and it's taking voltage off of each individual antenna in the pair, and then it's combining them to produce this what's called complex visibilities, which are then calculated to produce the image. And so in practice, it's usually a digital device. They usually sample at the Nyquist frequency, which is twice the frequency that you're studying. So If you're studying 400 megahertz, you sample at 800 megahertz, and then you're going to have then twice, whatever the number of samples that you have. And the correlator is going to take all those samples and put them together to form these, what's called visibilities, and then the visibilities are used to form the images. So it's, and I just threw this in here. If you actually work out the math, there's a whole lot of complex conjugate stuff, and it's pretty complicated stuff. And you can find some great lectures online that talk about this. You can find plenty of books and plenty of other stuff, but it's in practice pretty intense. So here's just a simple correlator, and it's the same drawing that I did before. The plane wave's coming in from the right, hits antenna 1 before it hits antenna 2. It's sampled here, and then in order to time them up the same, because it hit antenna 1 first, there's a delay down here built into the path from the electric signal. And so that electrical signal is going to be delayed so that it's going to match up with the signal that comes from antenna 2. Then they're going to be multiplied by each other, and that's literally multiplied. They take 3.2 volts times 4.7 volts, they multiply. And then they're going to integrate them over time. So this is the simple correlator, as we're going to see in just a second. I'm not going to get into this in any depth other than to point it out, is complex correlators. There's a little bit more involved, but this is just simple correlation. If you just do that, you'll find out the relationship between these two signals. And by the way, let's remind ourselves, what are we looking for? We're looking for a signal of interest. So whatever that is coming from space, and it's going to be in a sea of crap. And what's the sea of crap? It's going to be noise, right? So some of the noise is going to come from the world we live in. Some of it's going to come from noise from the system itself, from the receiver, or from the electronics that are all in it. So the signal to noise ratio is going to be initially terrible. The signal is going to be way low, and the noise is going to be way, way, way high. And so what we're going to try and do is pick out of this horrible noise thing. We're going to try and pick out these tiny, tiny signals of interest. And so that's the correlation that we're trying to do, is find the relationship between the signal of interest, not the relationship between the noise. And that's a key thing, as we'll see in just a second. So the way you do it in practice, and this is a little bit more complex, is we're going to take the two signals together, and we're going to do a fast Fourier transform on them, and then we're going to multiply them. And so what's the fast Fourier transform going to get us? That's going to get us the individual frequency components, and then we're going to multiply by then we're multiplying together. Or you could do it the other way around. You can multiply them together and then do the fast Fourier transform. Either way, you get the same answer. And so it doesn't matter. You can do it either way. And as we're going to see here in just a second, some systems use one way, some use the other. It used to be that everybody would do these on these massive arrays of hardware stuff. And I'm going to show a picture in just a minute of the one at the very large array that went from the 70s until the 90s. It required 50,000 watts of power, and it would do an unbelievable 1.7 terabytes of calculations a second. And it was doing it all in hardware. Nowadays, you can do it in software, much better, faster, cheaper. That's good news. The bad news is you still have to have the computers to do it. But now everybody does it versus software. And by the way, this follows the path of almost all electronics. If you're a ham radio guy and you opened up your radio in the 80s, you'd see a whole bunch of discrete components. You open it up now, you see a microprocessor. And that's because of how software correlators work. And the disadvantage of software, of course, is they're power hungry because there's computers and they're big. We won't talk about this much. I'll just jump right to it. And so this just shows the signals come in. Here's signal 1, signal 2. And in point of fact, you run it through a Fourier transform. That's what it looks like. Then you multiply it. Here's what it looks like in space. It allows you to be able to localize it in space. Or you can multiply them first and then Fourier transfer. Either way, you end up with the exact same thing. And so you say, well, why do we do it one way or another? And it has to do with number of antennas, and there's a bunch of stuff. But as you can see, the very large array uses the one where they multiply first and then do the Fourier transform. The Atacama also does that. Meerkat does it the other way around, does fast Fourier transform first and then follows it up. By the way, because this is software, you can get, so you have to do these calculations. Meerkat makes available their software correlator. And so I just throw that out of there, that you don't have to invent the wheel. You can get it, someone's already given it. All right, so now there's this notion of a correlator array. So you have the phased array, remember that's opening up looking at space. So what's a correlator array? So as opposed to what's typically a phased array. So what a phased array does is it forms a beam in real time and it looks at a particular spot. And so if I want to look at something, I aim at that. If I want to look at something else, I move it and aim at something else. But the point is I'm only looking at one thing at a time. When you do a correlator array, you take data from all your antennas all at once, and every time it samples, which is many, many, many times a second, you're simultaneously taking data from the entire sky at once. And that's a key point. You get the entire sky at once. And this is the point that won me over on trying to, if I'm going to do a phased array, of course I'm going to do a correlator array, because I get the entire sky all at once. Now I still have to be able to pull out and I can aim all that. That's part of the correlation. But the data is the entire sky all at once. And as I was pointing out here, some pictures. This is the picture on the left is the BLA correlator. That's enormous, 50,000 watts of power. The one on the right is one I just took yesterday when we got the tour here at Owens Valley. Their correlators, these are all computers, and this is their software computer. So this bank here, I mean, it's still pretty big and pretty powerful, but it's nowhere near the 50,000 watts of the very large array. Now, because you're taking the entire sky, by the way, this is also what this square kilometer array at South Africa does, is its correlator array. Unbelievable amounts of data. So here's an article that talks about where they are now. So they're going to do, what is it, 197 radio dishes and 130,000 low frequency. That's phase one. Phase two is 2,000 radio dishes and what is it, 1 million low frequency antennas. As a result, they're going to end up with 106 petabytes of data. So how much is a petabyte? I didn't even know. I had to look it up. It's 100 terabytes, and I'm sorry, 1,000 terabytes, right? And so it's, anyway, they're going to end up with 5 zettabytes, which is 1 billion terabytes. This thing by itself is going to be the single biggest data producer of anything in the world. So you're going to have a 5 billion terabytes of data that it's going to collect per year. And so think about the computation on that. So it's, oops, I just killed us off here. Oh, I did a.
Press the arrow towards you up the right.
Yeah, but I think I.
If you hit this thing, you'll go back in the slide.
That's the one I want. Okay, thanks. Okay, so that's the background, and I'll now get to my proposed telescope. So because you can get the entire sky at once, I want to do a correlator array. And it's going to be necessarily very sparse, and I'm going to use interferometry. So key requirements. I want to use off-the-shelf stuff if possible, because we don't have a lot of money and it's easier. And I also want to do real science. I don't want to just make a thing. I want to actually do real science. So just like schematically when I laid out my 611 megahertz one, you got all the parts. You got to have an antenna and preamp, receiver, computer, and recorder. Similarly, we're going to do that here. And here's schematically my proposed telescope. So I'm going to have an antenna. We're going to talk about these all a little bit more. You absolutely need to have a preamp. These signals are so weak, if you don't amplify them right at the antenna, you will absolutely lose them before you can even get them to any other processing. Then it's going to go through an A to D converter or time stamper, store the data, and then in option 1, this is all done on site, as I'll show you. And then it's going to be shipped off-site through a wireless system where it's stored again. It's going to go through the correlator, store the correlation data, and then make the image. Option 2, which is the one I think I'm actually more likely to do, almost all of this is going to be, well, all of it's going to be done on site, and I'll show you where in a minute, and it's going to be remotely controlled by me. So all the pieces are still there, but it's just slightly different. So why synthetic aperture? Why the sparse array? Just because that's the world that we live in. I can't fill in the tiles. So we're going to do this so I belong to the San Diego Astronomy Association. We have an observatory that's about 60, 70 miles east of San Diego, literally a mile from the Mexican border. So this is where it is. And here's a close-up of the key part of it. So these are all observatories along here, and then these are observatory pads. We have these two are the San Diego Astronomy Association. We own these. And we have a warming hut. And this is where I'm going to keep the hardware part of it. And by the way, let me just tell you about our group here. It's a large and active group. They do a lot of astrometry research, and they're looking for exoplanets. And they've got systems out there in some of those observatories that are better than probably most universities. And these guys are highly motivated citizen scientists. And recently, as I've talked up radio astronomy, there's a lot of recent, and I put latent interest in this. It turns out there's a lot of guys that are interested in radio astronomy, but don't know where to find it. And so part of my job is to do that. And we just recently started a little subgroup of radio astronomy. And so I just point that out. So out there at our complex, we're out in the middle of Nowheresville, but we do have 120 volt power available. Although it's possible, because the power requirements are not huge for this, that you could actually do this power with solar panels or batteries and inverters. So we're actually going to use 120 volts because we have it there. And so now what frequencies? So we've already seen this chart already today, but here's a chart that has a lot of interesting things that you can see, frequency versus flux density here. And I'm proposing that we do 50, 100, 200, and 400. And so why is that? Because there's a lot of stuff going on in the galaxy down at that end. And what is it? It's almost all, it's either thermal stuff, so black body stuff, bremstallic radiation, or synchrotron radiation. But there's a lot going on. Almost nothing spectrally here. And so you can look at all these, and it's easy to work with. And frankly, it hasn't been well looked at either. And that's another thing that is important to me. It's off-the-shelf components would work quite well here. So what's an ideal antenna? Well, it's a light bucket that gathers photons, in this case, light electromagnetic spectrum. And it's got to have a sufficient baseline for the desired resolution. And I'll talk about that. It's also got to have, as its beam width, you want it to have a large beam width, not narrow, which is counter to most antennas. Most antennas, you want to focus in on a specific area. When you do that, you get gain. So you lose gain here, but you're going to get a large beam width. And so how are we able to collect photons then if you don't get gain? You have a wide bandwidth, and then you integrate, and then maybe you make bigger antennas, or you make certainly more antennas. So that's how you collect more photons. So my antenna that I just starting off with this, the one I use for my 611 megahertz telescope, this is it front on, and this is its radiation pattern looking up at the sky. So the way you read this is here, imagine that you're in the center here, and then the ground is across here. And so if you look up here, it has, remember I told you it has about a 30-degree beam width. So if you went out here, half beam power on one side, out here is 30 degrees. And so it's not real great for looking at sky, even though 30 degrees is pretty good. So let me show you maybe a slightly better one. And so using antenna radiation pattern software, the 4NEC, I generated these, and I'm no expert in this, but I feel fairly confident that these are pretty good radiation patterns. So this is a standard dipole. And so so here's the ground plane. Here's looking straight overhead. So remember, most of the things you want to see are straight overhead. Notice this huge hole right here. So the dipole can't see straight overhead, right over its end. So this would be a terrible antenna for this. Even though it has good side lobes out here, it's not good for this. So the one on the right here is just a horizontal loop. And I just made a horizontal loop at 50 megahertz that had each side is 1/4 of a wavelength. And I put it at half a wavelength above the ground. And you get a radiation pattern now. Now look at this. That's relatively flat and wide. And this is, by the way, a far unperfected loop. And maybe if we did a better job of modeling the loop, it would probably be better. But that's definitely a candidate because I can get a pretty good view of the whole sky. Remember, I'm trying to get the whole sky at once. That gives me a pretty good look of the sky. One I think maybe I like even better is this turnstile antenna or the cross dipole. So you can imagine two cross dipoles, so crossing each other in a horizontal plane aimed up. And you can see here is its radiation pattern, and it's pretty good too. So maybe a horizontal loop, maybe a turnstile. So anyway, that's the antennas I'm thinking of using. And so I've still got to resolve what's the right antennas, what's the right frequency. And so smart people learn from experience. Really smart people learn from other people's experience. There are probably people on here now who are experts in antennas. I'm not. So the question occurs to me, and by the way, why 50, 100, 200, 400? Because I want to be able to get, like with your eye can discern colors, I want to see colors here. And so 50 megahertz would be 100. So that's why the difference here. And so if someone knows whether you can get a good broadband antenna, 50 to 400 megahertz, that gives you a good beam width, I'd be willing to hear what you have to say. So that's a problem in need of a solution. So what's the array itself? So I had to model one. So I figured I'm going to start with a 10 by 10 array. And my idea was no antenna could be closer than 2 meters. And so I created this crazy tool to help me to be able to do it. When I was done, I was able to put 26 antennas in a 10 by 10 array and not have them closer than 2 meters. And so imagine these turnstile ones on the 10 by 10 array. We're looking down on it from the top. When you do that and you combine all the different pathways, just like the very large array does, so there's these are 26 antennas. Remember, a very large array had 27. There's 351. I think 28 or 26 ends up, I think, 308. And so effectively, you get an antenna that looks like this. But notice its maximum separation is still only 14.1 meters, but still it's a 14.1, effectively it's a 14.1 meter dish, which is not bad for a starting point. Okay, but at the observatory there, not only do we have this land available, we have this other space up here available, and it's about 400 meters from one corner to the other that we could still use. Now, we haven't expanded that yet for the observatory, but it's our property, we can do it. And so my idea is then, okay, well, then let's put telescopes at the corners there and with about 400 meter separation. So down here is that 10 by 10 meter. And then now we have these further ones out. So now instead of a 14.1 meter separation, I have now 400 meter separation, and I have all these cross pairs. So it's as though I have a 400 meter telescope now. So remember, resolution goes up as your separation, your biggest separation. So you got to have a low noise amp. We just found out yesterday in the first talk, the keynote speaker, that non-cryogenic low noise amplifiers are now available, and they're not super expensive. So you need one of those, and that sounds like that's the way to look. You need an A to D converter. So you're taking these voltages and you're going to convert them to digital. Anyway, you just got to, practically speaking, moving analog stuff is just not going to work. It's got to be digital. So you got to be able to detect them. So detecting in our case isn't detecting as you normally do, like with a normal total power antenna. It's just converting the analog voltage to a digital voltage and time stamping it. And it's super important that you get really accurate and very narrow time spacing of the timestamps. So remember, I was showing you that you have to have femtosecond differences if you have 2 meter spacing to be able to tell the difference of stuff. Well, if your timestamp only is giving you millisecond resolution, you'd never be able to see those femtoseconds. So you've got to be able to have femtosecond resolution for this. And I'm talking about using a 14-bit A to D converter. And when you combine all these things, the 14 bits of the timestamp, 14-bit of the A to D converter, 12-bit of the timestamp, that gives you 26 or 28 bits. You can cover that with 4 bytes of data. So that means for every antenna, every time I sample, I need 4 bytes. And then you say, well, how fast are you sampling? And by the way, here's the problem. So nowadays you can get chip scale atomic clocks, and you can just buy them and they're super accurate. Unfortunately, they're only like at 10 megahertz. And so I need to be able to timestamp at femtoseconds. And I'm aware that it can be done, but I don't know how to do. So once again, people on here who maybe know how to take super accurate timestamps at the megahertz range and be able to parlay that into femtosecond, that's a problem that still needs a solution. If someone knows how to do that, I'd be glad to hear that. So you're sampling at 50 megahertz at the Nyquist frequency. That gives you a 10 nanosecond period. And remember I told you that when I showed you the picture of the plane waves coming in from above, at that sampling frequency, you're only able to have a ½ degree resolution from overhead. And that's just a function of that time of flight that it takes the signal to get from the first antenna to the second one. But notice that if I sample faster and faster, that overhead resolution goes down and down. So even though the Nyquist frequency is what you need to be able to produce the signal, if you sample faster than that, you get what I call sampling resolution. You get a better sampling resolution, which means you can look at more tinier spots in the sky. So how much data are you collecting? So at 50 megahertz, so you got to store this. And practically speaking, the storage limits for today are 5 terabyte disk drives, hard drives. And so at that sampling rate of 100 megahertz, how much data can you store? Well, you can get 3 hours, nearly 3.5 hours at 50 megahertz, which is also a reason why I wanted to sample at lower rates. The higher up you go in frequency, the smaller amounts of time, because you're sampling faster. So if you're sampling at 800 megahertz for the 400 megahertz signal, you only get 27 minutes worth of data versus 3.5 hours at 50 megahertz. And so as Dave was just saying, integration is important. Well, if I can integrate for 3.5 hours versus 27 minutes, I'm going to get a lot better data from that. And as I was pointing out, here's the storage. Now, it turns out these can actually have 5 gigabyte read-write times. And so I can get the data to them there, but I'm still limited by the fact that it's 5 terabyte. By the way, I just saw the other day, Best Buy was offering now 12 terabyte hard drives. So anyway, we talked about the timestamp. I got to be able to get the data from where it's gathered. So the idea is we gather it there at the observatory. We, by Wi-Fi, communicate it to that warming hut. And it turns out that Wi-Fi is no problem and it can easily operate at these frequencies. Now the problem is, how do you get the data from there somewhere else? And it turns out you can either go physically pick up hard drives and move them back, or you can try and send it by some kind of a wireless internet. The problem with that is, I'll show you, we're out in the middle of boony lands. The fastest we can get is 100 megabits per second, which is 25 megabytes per second. In order to download or to upload one 5 terabyte hard drive would take 4.5 days. And there's no way that I'm going to be able to get that. Remember, I've got 26 or more antennas. I just don't have enough time to be able to get that over the internet back to my central location to be able to process. So what I'm going to do instead is have those on site there, have the processing correlation done, and then take the correlation data, which will be many orders of magnitude less, and send that back. We're going to remotely control that that process, the computers, we're going to remotely control that. They're already doing that with the astrometry research that they're doing on site there. So that can be done. Okay, so now let's talk about long baseline interferometry, Tierra del Sol, that's the name of the sites. Okay, so this is super busy, but I just want to show you. So Andromeda is big in the sky, and in order to resolve it, in other words, be able to see it, the baseline separation would be 1/4 of a mile. So we're not quite big enough to be able to resolve Andromeda, even with our 400 meters. And then if you wanted to 4-time resolve it, in other words, you can, and I'll show you here an example. This is Andromeda. So if it was just be able to resolve it just by itself, that's this one big pixel, and there's no detail there. If I break it into a 4x4 resolution, that's 16 bits there, then I can be able to see a lot better if I do that. If I do that, I need to have 9/10 of a mile separation. If I want to be able to get the sun, be able to resolve the sun, I need 1/2 a mile, the sun and the moon. If I wanted Jupiter, I've got to have a baseline of 30 miles. So to put this in perspective a little bit, so here we are at Tierra del Sol, right, as you can see, we're right next to the next to the border. In order to be able to see the sun, so here's our, you can't even see, here's our little observatory. You don't have to be that much more to resolve the sun and the moon, but to get the 4-time resolution, you need about 1.5 miles, or 2 miles, 3 kilometers, anyway, out here. In order to get the M1 Crab Nebula, I'd have to be out here at 20 kilometers. And in order to be able to get Jupiter, I've got to be 175 kilometers. So the idea here is we would build a couple of these antennas here, and we would have at least some outliers, outriggers they're called. We would have them some distance apart. So we would either talk to somebody or maybe another club, have an association with them where they agree to put a few antennas somewhere out here, and they do their timestamp data. We bring it together, and then we're able to correlate it. We'd be using some later the XF or FX simulators. I told you that Meerkat, that they're making that available, so it would probably be something like that. You take the visibilities, you make the pixels, and then you make the frames. And so just a brief talk here about calibration, because we were talking about this. So how do you calibrate this? So historically, calibration, not just us, for everybody, they would look at a strong source, and then they'd calibrate. Then they'd say, okay, here's what I'm receiving. Here's what I should be receiving. I do that calibration. That's called Gen 1 calibration. And that gives you an improvement of about 1 in 1,000. So in other words, your error is now only 1 in 1,000 when you do that. Then maybe 20 years ago, they developed the concept of self-calibration. And that is, you use the target itself to calibrate. And that jumps you up to about 1 in 10,000. And now they're using the next generation, Gen 3, which takes you up to about 1 in 100,000. And so all of us as amateurs, we can clearly do, and some of us are already doing, Gen 1 stuff. But I think it's not that hard for us to do Gen 2 and maybe even Gen 3. And so this is something I'm going to explore a little bit more going forward. but I'm fairly confident that we can get that Gen 2 calibration even as amateurs. So maybe look for some more stuff on that as time goes forward. Here's some references and stuff. So when we talk about integration, what do? So you take these visibilities and you plot individual pixels in space for each frame. So each one of these things here represents a point of time. So you do the whole sky, you plot out here a whole bunch of individual pixels, you can think of that. And there's reference time 0, and then reference time 1. You add these on top of them, you just stack them on top, and you add it up. So the signal of interest is always there, and it's going to increase at a set rate. The noise is going to vary. And so the noise is not going to increase as fast as the signal. So the more you stack these up, the signal of interest will rise up out of there, even though both are rising, the noise signal and the signal of interest. The signal of interest rising much faster than the noise. And then by integrating this over time, you'll be able to see weak things will be able to jump up out of there. And so, as I said, I'm talking about time frames here of 3.5 hours, but I want to sample maybe once a month. And so you can stack over once a month. And so over time, you'll be able to see changes both within the time frame of your individual samples. So say in 3.5 hours, you'll be able to see changes, but you'll also be able to see changes that occur over months or years by being able to compare those. So that gets to the science part here, which is really at the end here. It'll measure the time varying radio phenomena on scales of even microseconds up to an hour, and then also several months. And then also so what can you see with that? Maybe pulsars, maybe some counterpart to the optical astronomy, exoplanet stuff, maybe. You can definitely see changes in solar and Jupiter, I think, and other transits. So Harvard did something where they were looking in 2004, where they were looking at just transient stuff, and they were able to observe most of the stuff they saw was related to the sun. And that's just weird things that were happening on scales of a few milliseconds up to several minutes. And I think we should be able to see that with this as well. And then a sky survey. So this is an actual sky survey that was done. Can't remember who did this one, but this is an actual one. So we could build up our own sky survey. I don't think anyone's done 50 megahertz. And so that would be, and then if you do it in color, you could have, a color assigned to 50 and 1 to 100 and so forth. You'd be able to get the color out of here. And I think it would be cool to have a sky survey in color. And so anyway, that's it. So where can money come from? I was at a conference here recently and NSF was there. And at the end of the conference, they had time. So I went over and hobnobbed with them. And they told me 2 things they look for funding. You have to have a scientific purpose, and they want inclusion. And that is as many people as you can get involved in things like academic institutions and other groups. And so I think we have a scientific purpose, needs to be refined. Inclusion, I've been working with San Diego State University to be able to, they seem to have an interest to want to collaborate with us on this. Frankly, UCSD does not. And maybe there's a little snobbery or something. But, and I've also talked to a couple other astronomy groups around, and there's some interest in this. So maybe there's a way to form some kind of a group and we all get together and maybe we could get some NSF funding. So next steps, I got to decide on frequencies, pick the antennas and all that, develop the collaboration. I'm going to build 3 prototypes so I don't end up making a whole bunch of the wrong thing. So I can put 2 in an east to west direction and 1 in the north, and that'll allow me to be able to test the concept out. So anyway, that's where we are. Questions?
Yeah, lots of questions. But anyway,
I got one from Wendy. It says, when you complete your calibration, let us know.
okay. I got a couple of questions, 3 questions here.
Can everyone hear Dave asking the question here?
Right.
Here.
Okay. First of all, regard to talking about visibilities, of course, when you correlate and integrate, and as you integrate, as you said, as you integrate, your noise relative to your signal goes down, and your signal becomes more and more prominent as you go along. But what we're looking for when we do that kind of observation is you're not looking for visibilities per se. You're looking for a sky image. And one of the basic facts about radio astronomy is that your sky image is a Fourier transform of your visibilities. And that's why your visibilities are your raw data, but your sky image is what you're really looking for. And you can usually cut down on the amount of data you have to store at the end of the process when you actually do your Fourier transform and get your sky image. It is a lot more compressed than the original visibilities you actually got off of it, because that was so much data that you basically have to throw away a lot of it because after you have done the analysis on it, it's much more compressed. So that's a very important thing when you get to the end of this from interferometry. Most of the time when you've done this, as a result of all of the gaps in your data, as you talked about in yesterday's talk with Vikram, you have a lot of holes in your data that cause a lot of artifacts to appear, and you get a dirty image out of all that process. And you have to go through what is called this cleaning process in order to get your clean image. And this is a very burdensome process as far as analysis goes, because cleaning is a very sophisticated algorithm. Some of it's very hand-wavy and voyeuristic, and something that you would like to get rid of if you could. And as Vikram pointed out in his talk yesterday, they found ways of doing that by building this deep synoptic array, which he's going to put out in the desert back there, which will eventually enable them to get rid of the cleaning step and get a much clearer, cleaner image out of the sky directly from a very well-placed interferometry array of 2,000 telescopes, the way they plan to do it. So this is something that we've learned as far as the work they're doing here at Caltech. And another step I wanted to suggest to you is, I think your setup there in San Diego is really impressive. I really like what you're doing down there. I think that's a really wonderful work that's been going on down there. And at some point in the future, we would love to hold a Western conference down in the San Diego area that would really, expose the people down there to what SARA can do for them and how we can, help them out with the members of SARA and everything, because I think it would be a great place to have another Western conference at some point in the future. So I'd like to know that. Okay, thank you.
So just addressing that last one first, everyone likes to come to San Diego, so you can bring your families. So yeah, that's actually a good one. As far as all the cleaning and the dirty image and stuff, I debated whether to put that in, and I was already close to my time anyway, and so I didn't put it in. But yes, I'm aware of all that. And then, as you pointed out, Vikram did point out some tricks here, and anything you can do to reduce the number of calculations will be great. So I found some papers on exactly what you're talking about, and I need to go back and look at that a little bit more, maybe even ask Vikram.
I was in a question. Your question about your timing resolution and your timestamp.
Yeah.
I'm not sure you need high resolution timestamp. What you need is a low jitter sampling clock, right? So that you know that this sample occurred exactly when you think it did. Not necessarily trying to track to the femtosecond when you sampled it, but just
so as long as I'm sampling, as long as it's stable.
A very low jitter sample clock is, I think, what you need, not necessarily a timestamp to that resolution.
Okay.
It simplifies the problem sometimes.
The way the VLP, very long baseline array works, and this is fascinating. Incidentally, you talked about the VLPA in your slide in your talk there. You had 20 down for the number of antennas, but it's actually 10. And they have 10 antennas spread all over the Western Hemisphere, pretty much, from Mauna Kea to Virgin Islands. And the way they do it is they have very, very, very accurate clocks at each station. And they keep track of their time with a very, very low resolution on that. And then timestamp every single set of samples they get out of each station when they do an observation, and then they get together physically all of these different data packages and run them offline through an analysis procedure at SARA and produce the result at that point from all of the data packages that they've gathered each individual antenna. And each individual antenna is located precisely in 3D, 3 dimensions, because the curvature of the Earth is so prominent throughout all these locations that go all different directions, from Mauna Kea to Virgin Islands to northern Washington State to down in Texas to all over the place, where they have all these 10 antennas. And they can do the 3D location of these things and produce really, great images out of this. The analysis process is really intensive.
So essentially, what I'm doing is I'm mimicking what they do there, but I'm doing it each individual antenna, even though we're close together. So we're not going to be physically connected. And so because of that, because we're taking that data just like they do on the very long baseline interferometry, because we're using that same thing, you can locally, you can do that remotely. So all I need is some farmer I have a friend that's a farmer in Minnesota. If he allows me to put a dish there, as long as I can hook it up to the power and I can get internet from him, that's a signal to me. And then I'm going to do the exact same thing, bring the data back, and I'm going to do all the correlation and the image processing and all that. I'll do that on site. That's the site. So basically that's what I'm doing. I'm replicating the VBLI only on a small scale. And so that was actually the model of it.
Great. Yes, definitely.
Great. Okay.
Question.